Hi, I'm Marius from Mental Model Space, and this is part 3 of Introduction to Systems Theory. In this video, I'll be talking about competing feedback loops. I'll first start out by describing thermostats, where we have two competing balancing feedback loops, and then move on to populations and capital stocks, where we'll have a reinforcing feedback loop competing with a balancing feedback loop. So last time, we familiarized ourselves with the behavior of both balancing and reinforcing feedback loops. We saw the example of coffee cooling or warming for balancing loops, and the example of an account value growing for reinforcing feedback loops. And we learned that in general, balancing feedback loops try to bring the stock to the desired level, and in that sense they're goal seeking, while reinforcing feedback loops amplify behavior, leading to exponential growth or collapse. And we also asked ourselves the question, what would happen if both of these behaviors collide? And this is the question we'll try to answer in this video. The first system that will help us answer this question is that of a thermostat, where we have two competing balancing feedback loops. And we can model this thermostat system by the following system structure. Basically, it's just a one-stock system with a single inflow and a single outflow, and both the inflow and the outflow are regulated by balancing feedback loops. And since this diagram is a little more complex than the ones we saw previously, I'm going to go through each element separately so that we can understand what's actually going on here. Our main stock, the room temperature, basically just represents the amount of heat that's present in the room. And we have an influx of heat that comes from a furnace, and that's regulated by our thermostat. And we also have an outflux of heat, which is basically just a passive cooling process. So no matter how well we insulate our house, we'll always have some amount of heat that escapes. On the left-hand side, this balancing feedback loop's basically our thermostat system. And we have this one parameter, the thermostat setting, and that's the temperature we set our thermostat to. And what the thermostat then tries to do is it finds the difference between that desired setting and the room temperature, and then if the difference is large, it'll activate the furnace a large amount and we'll have a larger influx of heat. And if the difference is small, then the thermostat will only activate the thermos a small amount, we'll only have a small influx of heat. And this influx of heat is also determined by the furnace strength. So if we have a very powerful furnace, then the influx of heat will be correspondingly large, and if our furnace is very weak, then the influx of heat will only be small. On the right-hand side, that system is basically the same as we saw with coffee cooling, where we have this parameter of the outside temperature, and the difference between the outside temperature and the room temperature will dictate the amount of heat that escapes from the system. This escape of heat is also dictated by the insulation strength. So if our house is very well insulated, then only a small amount of heat will escape. And if our house is insulated poorly, then after a large amount of heat will escape. So we have these two parameters for each balancing feedback loop that sort of dictate the inflow or the outflow. And sort of the two parameters that are in competition with each other are both the furnace strength and the insulation strength. And this is intuitive. If we have a really good furnace and our house is really well insulated, then after we don't have to heat as often. While if we have a bad furnace and our house is poorly insulated, then we might not even manage to keep heat in the house, right? And the other two parameters that are competing with each other are the thermostat setting and the outside temperature. So if the difference between the thermostat setting and the outside temperature is small, so basically, if it's like the same temperature outside as we have our thermostat set to, we don't even need to heat. But if the difference is large, we have to heat a lot. Before thinking about how this system will behave as a whole, we can start by just considering each of the balancing feedback loops in isolation, because we're already familiar with their behaviors. So if we just look at the left-hand side and that balancing feedback loop of the thermostat and furnace, and we have a room that starts at a temperature of 10 degrees Celsius, and our thermostat is set to 22 degrees Celsius, we see expected behavior. The room will just continuously warm up to that target temperature of 22 degrees Celsius. And conversely, if we just look at the right-hand side, and we have a room that starts at 22 degrees Celsius, the room will just progressively cool down until it reaches the outside temperature, which in this case is 10 degrees Celsius. So the question now becomes, what happens if we combine these two familiar behaviors and look at the behavior of the system in its entirety? And this behavior is plotted in the following graph. Again, we have the thermostat set to 22 degrees Celsius, which is the gray dashed line. And we have a case where we have a strong heater, which is the dark blue line, and a case where we have a weaker heater, which is the light blue line. So the first thing we notice is that we again have this familiar behavior that balancing feedback loops produce, where the value approaches a certain equilibrium value and then stabilizes there. What might, however, be counterintuitive is that this equilibrium value is actually below the temperature we set our thermostat to. And the reason for this is that basically some amount of heat will always escape at the same time as the heater is heating. So you never actually manage to reach that magic thermostat setting level. So this explains why if we want to have a certain room temperature, we have to set our thermostat slightly above that. And if our house is poorly insulated, we have to set it more above the value we want than in a better insulated house. We also see in the two different curves, so the dark and the light blue, that if we have a weaker heater, the equilibrium level is further away from sort of this thermostat setting than if we have a stronger heater. And this makes sense intuitively. I haven't shown it in this graph, but the same thing will apply for insulation. So if we have a house that's well insulated, it will resemble more the curve of the strong heater. And if our house is poorly insulated, it will resemble more the curve of the weak heater. So basically, if we have two balancing feedback loops, the combination of these loops will behave like a single balancing feedback loop, but it has a new target level. And this target level will be determined by the relative strength of each balancing feedback loop. So far, we've assumed that the outside temperature remains constant at 10 degrees Celsius. But obviously this isn't very realistic, since the outside temperature will also vary over time. And we can update our model accordingly, and what we get is the following behavior over time graph, where the dashed gray line represents the outside temperature profile. So we see that the outside temperature starts at around 15 degrees Celsius, then progressively declines to below 5 degrees Celsius, and then goes up again to 15. And again, we have these two cases, the case of the strong heater, which is represented by the dark blue line, and a case for a weaker heater, which is represented by the light blue line. What becomes immediately obvious from this plot is that varying the outside temperature also affects the inside temperature. And this effect is much more pronounced in the case of the weak heater than it is for the strong heater. In the case of the weak heater, we see that as soon as the outside temperature starts to plummet, so does the inside temperature. And this is basically just because the furnace is not strong enough to sort of compensate for this colder outside temperature. In the case of the strong heater, we see that the more powerful furnace can easily sort of keep up with the declining outside temperature, but there still is a slight amount of curvature in that dark blue line. The same thing will also apply to insulation strength. So if we have poor insulation, the curve will more resemble that of the weak heater. And just as a foreshadowing remark, if we have bad insulation, we can't necessarily compensate it by just installing a more powerful heater. We'll see that this will basically just result in like large fluctuations in the inside temperature. And this has to do with the concept of delays that we'll be introducing next time. Now that we hopefully have a good understanding of what happens when two balancing feedback loops interact with each other, we can shift our focus and see what happens when a reinforcing feedback loop competes with a balancing feedback loop. This situation is the case in the case of populations, and we can model a population using systems theory as follows. So we have one central stock, which represents the number of individuals in the population, and individuals can join the population through births and exit the population through deaths. The number of births is controlled by a reinforcing feedback loop. So basically, the larger our population is, the more people there are in the population to give birth. So correspondingly, the number of births will be higher. And the number of births is also controlled by the fertility rate, which is basically just a way of expressing how many percent of the population is going to give birth in a given time. If we look at the number of deaths, this is controlled by a balancing feedback loop. So the larger the population is, the more people will die. And if we have a small population, there are less people who can die, so the number of deaths will be smaller. And the percentage of people that will die is determined by the mortality rate. Here in this simple model, we're making the assumption that basically people are equally likely to die when they're young as when they're old. In reality, this isn't the case, but to illustrate sort of simple population behavior, this is sufficient. In order to investigate how this system, where we have competing, reinforcing, and balancing feedback loops, behaves over time, we can consider the following scenarios. So in the first scenario, the fertility rate is greater than the mortality rate. And so as expected here, we have population growth. If we look at the behavior over time graph, we see our population starts out at about 6 billion and then progressively increases in an exponential curve type fashion, so that by the year 2100, we have a population of about 22 billion. In the second scenario, the fertility rate is lower than the mortality rate. And here, again, as expected, we have population decline. So if we start out with 6 billion in our population, by the year 2100, at this rate, we'd have about 4 billion people left. And this behavior is reminiscent of a balancing feedback loop curve that will eventually reach its target, which in this case is a population of 0. So if the fertility rate always remains lower than the mortality rate, eventually the population will die out. In these previous two scenarios, we assume that the fertility rate and the mortality rate remain constant, but this doesn't necessarily have to be the case. And so in this final scenario, we look at a case where we start out with a fertility rate that's higher than the mortality rate, and then it slowly declines until it equals the mortality rate. And sort of this is a model for, we see in the real world that as countries develop, their fertility rates decrease, and sort of this models that type of behavior. So in the behavior over time graph, we see that the population initially increases a little bit, but then the fertility rate drops and equals the mortality rate, and at that point, the population will just remain stable throughout time. We can play around a bit more with varying the fertility rate over time and, for example, get a graph that looks like this, where in the first section, the fertility rate is greater than the mortality rate, which results in population growth. In the second section, we have a fertility rate that's the same as a mortality rate, so we have a population equilibrium. And then finally, if the fertility rate is again greater than the mortality rate, we again have population growth. So in this plot, we see what happens when we vary the fertility and keep the mortality rate constant. But of course, we could also imagine that we can vary the mortality rate over time and keep the fertility rate constant. Then the mortality rate itself would affect how the system behaves as a whole. Or we could imagine varying both the fertility rate and the mortality rate, and then sort of their relative values to each other would affect how the system behaves as a whole. Because fertility and mortality rate directly influence how strong their corresponding feedback loops will be, and the relative strength of the feedback loops to one another determines the overall system's behavior, we call fertility and mortality the drivers of behavior for the system. If we think back to our thermostat example, we also had drivers of behavior. In that case, it was things like the furnace strength or the insulation strength, which caused their corresponding feedback loops to be weaker or stronger. In the case of populations, it's particularly interesting to ask what drives the drivers. So if fertility and mortality aren't constant but vary over time, what affects them to change? So in the previous slide, we had an example where the fertility rate decreases as the population increased. And this was as a model for as countries develop, their fertility rate declines in general. But we could also imagine that the mortality rate increases as the population increases. So this could be an effect of overpopulation, for example, so that we have more spread of disease, etc., if people are living in cramped conditions. And if this would be the case, that if the mortality rate goes up when the population goes up, we'd actually see a larger increase in death rate than we would expect if we just had a balancing feedback loop and had a constant mortality rate. The next system that we'll look at that has competing, reinforcing, and balancing feedback loops is that of capital stocks. So when we think of capital stocks, we could think of actual physical capital, such as factories and machinery, but it could also be more abstract, like financial instruments that we buy on the stock market. The amount of investment into the capital stock is controlled by a reinforcing feedback loop. This is similar to the situation we saw in the case of a bank account. We have a parameter called an investment fraction, which is sort of like the interest rate, which tells us how much of our annual output we reinvest into the stock. And we also have a parameter called the output fraction, which tells us how productive our capital stock is at producing earnings. The depreciation is controlled by a balancing feedback loop, which depends on the capital lifetime. So if our capital lasts a very long time, then we have a correspondingly small depreciation rate. And if our capital is very short-lived and breaks all of the time, then we have a larger depreciation rate. Although this system seems superficially different from populations, so basically there seems to be little in common with people and with machinery, right? Because the system has a similar feedback structure as that of populations, this will lead to basically the same behavior. We can show that this is indeed the case by looking at a behavior over time graph. So in this following graph, I've plotted the physical capital value versus time. And in dark green, we have the capital lifetime set to 20 years. In the sort of medium green, we have it set to 15 years. And in the light green, the capital lifetime is only 10 years. So what we see is if we have a long capital lifetime, we have an increase in capital value over time. And this increase sort of resembles this exponential type curve we saw in the case of population growth, where we had the fertility rate being higher than the mortality rate. If we look at the curve where the capital lifetime is only 15 years, we see that the physical capital stock remains constant at $100,000. And this resembles the case where we had the fertility rate equaling the mortality rate. And finally, if the capital lifetime is short and only 10 years, we get a decrease in the capital stock value. And this resembles the case where we had a higher mortality rate as compared to the fertility rate. So in general, the drivers for this system are the output fraction, the investment fraction, and the capital lifetime. In this plot, I've just varied the capital lifetime, but we could vary these other parameters and we'd see similar results. So basically, this capital stock system is very similar to the populations because we have these drivers which influence the relative strengths of the individual feedback loops, and the relative strengths of the individual feedback loops in turn determine the overall behavior of the system. So either the reinforcing feedback loop can dominate over the balancing feedback loop, and we get this familiar exponential type growth that we saw in the population growth and also here with a 20-year capital lifetime. Alternatively, the balancing feedback loop can dominate over the reinforcing feedback loop, and in this case we get this decline we saw in the case of population decline, but also here in the case of 10-year capital lifetime. And finally, they can also cancel each other out if they're exactly the same strength, and then we just get a constant stock value. Before concluding, I would like to consider some questions that we can ask ourselves if we're trying to determine how good our model is. We saw in this video how the overall behavior of a system is determined by the relative strength of the feedback loops in that system, and that the relative strength of those feedback loops is in turn determined by these driving factors, such as the mortality rate or the fertility rate, or the furnace strength or the insulation strength. And because these driving factors are ultimately what will have a huge influence on how the system actually behaves over time, it's worth asking some questions about them. I've taken the following questions directly out of Thinking in Systems, and I think they nicely challenge our assumptions about the driving factors and how they are likely to impact the system's behavior. And the first question is, are the driving factors likely to unfold this way? So if we think back to populations, we could ask ourselves, how likely is it that the fertility and mortality rate are going to remain constant over time? Or how likely is it that the fertility rate is going to decrease as the population increases? The second question is, if they did, would the system react this way? So if we know for a fact that the mortality rate is going to do something like increase over time, is the system actually going to react the way we're predicting it to react if this were the case? So this basically challenges how we're modeling the system based on these driving factors. And finally, what is driving the driving factors? So we considered this question before when we looked at populations. So if the population size actually has a direct effect on the fertility rate or the mortality rate, this would generate a new feedback loop that we hadn't considered so far in our model, and this will drastically influence our model system's behavior. So when we're confronted with a new model, it's always good to keep these types of questions in mind when we're trying to evaluate how plausible it is. And with that, we've already reached the end of today's video. I'd like to briefly recap what we've learned today. So we saw first that two competing balancing feedback loops cause equilibration at a new level depending on their relative strengths. So basically, two balancing feedback loops together generate a new balancing feedback loop that just has a new equilibrium level. And then we saw that in systems where a reinforcing feedback loop competes with a balancing feedback loop, the stronger loop can dominate, and then we get the behavior that's characteristic of that type of feedback loop, or they can cancel each other out exactly, and we just get a constant behavior over time. We also saw that the relative strength of feedback loops is determined by their drivers, and we learned to ask, what is driving the drivers? Thank you for your attention. You can find these slides as well as other written posts at my website at mentalmodel.space. If you've enjoyed this video, feel free to like and subscribe. And with that, I hope to see you next time for part 4, where we'll introduce the concept of delays and see how that influences system behavior.